So if you're starting in H band, the recommended exposure time is 120 seconds, and you want to have 16 reads. 16 reads and dither pattern ABBA.
Yep. But all set up. And then for K, it's 180, right?
K is 180. Yes, that's correct. How are you doing, Jamaica? How are things today?
I'm doing well, Bryce.
Oh,
Thank you.
I can hear you all right now. Let me, so Matt, do you have everything kind of handled right now?
Yeah.
Okay, I'll be right back. I have to go run and get something.
Okay, we'll be here. Thank you.
So Leo here will keep you company. Is that okay, Leo?
Yeah.
Hi, Leo.
Mika, how are you?
Good. Thank you. How are you?
I'm good. Well, we're getting things set up for spectroscopy now. So hopefully this will be exciting for everybody.
I have no doubt that it will be. Thank you. We certainly appreciate all the amazing support, the fantastic Keck staff, as always.
Well, thank you.
Are you able to tell us a little bit about the process of getting ready to do spectroscopy if you have a moment?
Oh, absolutely. Do we need to sort of talk about what spectroscopy is, or do we want to go over how to
Please do.
prepare? Okay. So spectroscopy is a little bit like playing with a prism. So what we're doing is we are taking a bunch of light into our telescope and dividing it into the different colors or wavelengths of light. So so this light will be divided into, it's sort of like a rainbow, but in infrared in our case. That way we can actually take a look at what specific color or wavelength each little bit of light is, and measure how much light is coming off of it at that particular wavelength / color. So we can use this to determine what something in space is made out of. So for example, when I studied galaxies using the same instrument, we were measuring how much oxygen, how much carbon, how much nitrogen, and how much hydrogen were in different galaxies. And so that's normally what spectroscopy is used for. You can also use spectroscopy to measure how fast something is moving. You can do that by measuring how offset a particular packet of light is from where it should be. So if something, say, if you have listened to a siren or a train, if you'll notice that the pitch of the sound will change depending on whether it's moving toward you or away from you. Light does the same thing because it's a wave, just like sound. So depending upon how offset it is, you can tell how fast something is moving towards or away from you. So there's a number of things spectroscopy is useful for. But spectroscopy is a little bit difficult to actually do in science. So we need to measure a few things. Oh, was there a question first?
Oh, no, I was just going to say the, you know, the measuring things moving towards us or away from us. This is redshift and blue shift. Well, towards us, it's
Exactly.
blue shift, redshift. Right. Okay. I was just wanting to confirm with you.
Oh, yeah. No,
But then, yeah,
exactly.
please continue.
Okay, so if we want to do spectroscopic measurements, though, we need to do a few things. We need to measure the response on the chip. So we do that by taking what we call flat images. So we just take our telescope, point it to a flat white lamp, and we determine which parts of our detector are a little more sensitive than others, so because they will appear a little bit brighter. And we can use that when we look at our final images to determine a correction to make sure we're getting equal response in all of our pixels. But we also need to figure out at what part of our detector represents what wavelength of light. So what we have to do is we have to measure, here, I'll point this out. Can you see my cursor? There we are. Yes, so I'm moving around. So we have two
Yes.
different lamps we can put on, neon and argon, and they will emit packets of light at specific wavelengths that we know from laboratory experiments what that wavelength or color is. So when we do that, we can actually compare to the data that's taken to determine what specific wavelength that light is at. And so we can know if something is offset or what particular element we're looking at.
Oh, that was brilliant. Thank you so much. Thank you so much. And just for those who watch us who watch this recording, could you please, you know, just again, tell us your name and your role?
Oh, my name is Leo Alcorn.
Here's a link.
Oh my God. Thank you. I
Yay!
am a staff astronomer here at Keck. I specialize at the moment in MOSFIRE. I'm actually their newest staff astronomer. Just moved here from my postdoc in Toronto, even though I'm originally from California.
Wow, congratulations.
Yeah, thank you. And so there's a few different support staff. I am sort of the liaison, the person who connects the astronomers who are taking data to the individual instruments that they're using and make sure that they get the best possible data using that instrument. And then we have Tony, who is actually moving the telescope. I guess I can switch you around here so you can see Tony here working hard.
Hi, Tony.
They're saying hi, Tony.
Thank you.
So he's the one who's actually moving the telescope.
Hello.
And is in charge of making sure that we get the right offsets, that we get the right angles on our slits. So it's a whole team effort here.
Amazing. Thank you so much. Thank you so much. And it was a pleasure to meet you.
Yeah, same here.
Hey, how's it going?
We're so good. She's getting us started on the right foot, Bryce.
Oh, great.
Talk about elements, talk about redshift, blue shift, all sorts of things you can measure with spectroscopy.
Oh, yeah.
Just by basically
That's right.
rainbow of infrared light.
Matthew, how's it going?
It's pretty faint.
Well, I thought I saw a trace a second ago.
Yeah. I saw it in the different image. But it's not like yesterday where we could really see it. And it's right here, right?
Yeah, so it's UD 545. Here.
Are you all doing the standard style or are you doing science?
We are doing science right now.
Okay. Out of curiosity from both me and our viewers, what particular spectral features are you hoping to see?
We
For these ones, we're hoping to get detect water ice at 2 microns.
Ooh,
which is a combination band, which means, when you're looking at vibrational spectroscopy, you're looking at methylation molecules that they forward. And so this is the sort of the closest of the sort of strong-ish modes we can see of water in the infrared. The 3 micron is not really visible from the ground all that well, because of course we have water vapor in our atmosphere.
Matthew, can you talk to your camera? Can you have your camera on? And because I don't think people can see you talk.
River view.
But make sure you mute. Yeah.
Let me take care of that.
So here's something funny. You can mute your mic, but to see if it will come through here on my mic.
Yeah.
So if you keep talking, but mute your mic on your laptop, but unmute the thing that lets you talk to the observer, and then we'll just have it kind of feed through this mic here.
Okay. How does this sound?
Can y'all see? Can y'all still hear Matthew? Okay. So Matthew, say something.
Hey, can you hear me?
We can hear a little bit.
Okay.
I think I'll do this through the laptop. We'll be fine.
Yeah.
I'll switch back and forth.
Yeah. Well.
Oh, y'all are great. Thank you.
Yeah. So as I was saying, we're for these objects trying to look for the 2 micron water ice feature, which is going to tell us just about whether water ice is present on these objects. It's the best one that we can see from the ground for detecting the presence of water ice. I mean, if you think about it, we have water in our atmosphere, so it's very difficult to actually see it if we're trying to look for it. So the 2 micron, by virtue of it being very broad when we're looking at ices, allows us to sort of see part of that absorption feature dip, despite the spectrum of molecular water in our atmosphere blocking part of that wavelength range. So we sort of in the K band and H band see part of that absorption, so sort of the spectrum going down a bit. And that's what we're trying to see. We're just trying to see if these are sort of more water ice rich types of objects or the more methanol rich types of objects. You can actually see methanol at 2.2 microns as well, which we don't have a lot of in our atmosphere, and not any. And then a lot of these objects really far out in the solar system have this methanol ice, as it turns out. So trying to look for whether these objects are more like organic-y or water ice rich is the goal of our spectroscopy today.
Thank you for catching us up on everything, Matthew. That's brilliant.
Yeah, no problem. I think we actually can see the trace now, Bryce, if you want to really quickly show them, show the DS9 window.
Yeah, sure. Give me a second. Go. Just setting up my air mass chart. I think the next target we want to do is maybe this 2007 RG1, and then
Yeah,
we'll
that's
look at the Earth asteroid.
Yeah, that sounds about right.
Okay, yeah, because we want the better air mass for that one for sure, because it's super faint.
Exposure complete.
This one's also, yeah, all these are pretty faint actually. They're all around 20-ish. But yeah, let's look at the trace.
So you just missed it because now we're doing B minus B, so this we're not going to see it, but wait for the next exposure. So 2 minutes and we should see it because
there it is.
There it is. Okay.
Yeah, that's beautiful.
Yeah, it's pretty nice.
Yeah, so that's just a rainbow of light coming off of a distant object.
Let's see here. Zoom if it's from. We do have a slight problem. The slight problem is that I don't know where the card keys are.
The car keys.
Yeah.
Oh no.
I'm hoping Laura makes it. But if they are not, well, then
That looks like we got another object on the slit by accident down here.
yeah, but I mean that's
Yeah, there's some star. unavoidable.
Where do you see that other object at?
So it was right down here. You see another horizontal line coming through. And that's probably just some background star galaxy. Who knows?
Oh, I see. I see.
Yeah. We just specifically put the object right here. And it's quite faint. It's 21 magnitude. And we got it the other night. I just want to get it again so that we have, decent signal to noise for it. And, the features we were looking for here, these aren't emission lines. These are very sort of broad features. So in terms of this image, the feature probably would go from somewhere like here, it would go from here to here. So we would expect this part to be not as bright as this part of the trace. And so, yeah, we're probably going to take all these pixels and just sort of sum them together and just pick out a few points total. So a lot of binning down will happen to get the final results, just because we're sort of trying to answer a binary question, like, is there water ice or not? And can we detect it at, say, like a 5, 10, 20% level, right? It's more trying to get a bunch of objects and seeing what the population looks like rather than a careful study of any single object.
Ah, okay, that makes sense. And these are all the targets tonight, all in the Neptunian system and they're Trojans, or are there some other targets in there?
So we had to do a backup plan here because the Keck instrument that we're using is in spectroscopic mode, and we can't, for the Neptunian Trojans, we want to use it in imaging mode, but because it's in spectroscopic mode, it's now, it has to be used in this mode for now. We changed our science plan a bit, and we're going to be targeting objects that are a bit closer to the sun. So these are centaurs, right, Matthew?
Yeah. Yep.
So they're in between the trans-Neptunian system and the terrestrial planets, and really between Jupiter and the trans-Neptunian system. So definitely the outer part of the solar system still, but a little bit closer than the Neptunian Trojans.
Got it. Okay, thanks for that update. Okay. Centaurs it is.
Centaurs, yes.
Yep.
The half horse, half man creature.
Yes.
Okay.
And yeah, because these are a bit brighter, we can afford to actually do the spectroscopy on them. We're about halfway through our, I think, H-band sequence, and then we're going to move to K-band and then on to our next target. And so I think H to K-band covers something on something like 1.6 to 2.4 microns. So that's far, far past where our eyes can see.
Oh, definitely.
Yeah. And yeah, from the ground, typically this is as far as people go. There's also L band and M band, but those you can only do for the really, really bright stuff. I mean, this is never gonna, you're never gonna get this kind of stuff in L band just because the sky is too bright.
Oh, there's the trace again.
Yeah, because this is.
So I'm gonna show the audience the conditions right now. So this is something that you're constantly checking on when you're observing. Are the current conditions. So right now we had a seeing measurement earlier. It was 0.8 arc second seeing. Another thing you look at is the cloud cam. See, to make sure the sky is still clear. So it looks like the sky is still pretty clear. There's the moon. So there's the moon rising there. I don't like this movie. I like it just to show the latest frame, but it's stuck in this annoying movie.
Me too.
Yeah, just show the latest frame, please. There we go. So that, yeah, this is what the sky looks like outside. It's the moon is nearly full, so 99.8 illumination. So it just kind of blots out the sky. But in the infrared, the sky is actually very dark in the infrared, even full moon. So that's why all the instruments that we use during bright time, we call when the moon is full bright time, tend to be near infrared instruments. Because the sky brightness is not affected by the moon in the infrared wavelengths as it is in visible wavelengths.
Yeah.
So we're looking at here. This is the weekly setup. We're still taking data, right, Matthew?
Yep.
So this is the weekly setup. So they tend to like to use, right now it's bright time, so they tend to like to use infrared instruments. So this is on Keck I, and the right side of this is on Keck II. So right now we have MOSFIRE tonight. It's infrared spectrograph. And on Keck II, they have NERC2, which is a high resolution infrared camera that uses adaptive optics to take images of the sky at better resolutions than Hubble, even better than James Webb at the shorter wavelengths.
Yeah.
And then tomorrow night, they're using the Keck Planet Finder, which is like a high resolution spectrograph. That's visible, but they're looking at targets that's very bright. So even in the full moon brightness, it doesn't affect them that much. But on Keck II, I don't know what PCS
Exposure
is, but
complete.
NIRES is a near infrared spectrograph. KWCI is also an infrared spectrograph. And so we're all in the infrared right now, except for these Keck I super high resolution spectrographs. They're looking at super bright targets. They don't really care about the full moon. But in general, yeah, NIRES is all in Keck II. In general, that's also an infrared spectrograph. In general, during bright time, we like to have the infrared instruments on. So let's look. We just finished another exposure, Matthew. Is this a B minus B or A minus A? Let's see.
This must have been an A minus A, I believe.
Yeah, let's look at it. Press the tab button there. Yeah, so it's an A minus A. So that means that we're not going to see the trace. So in infrared, you have the sky background, and the heat from the instrument makes the background so bright that you have to dither the telescope between exposures. And I'll show what the setup is. So this is the current setup. We're still taking data, right? So we're second exposure of the second repeat. Okay,
Yeah,
very good.
3/4 of the way through.
So we use a pattern called ABBA. It's a dither pattern. Let's see. I think I have the dither website open up. So this is like all the breakdown of all the dithers. So this is a mass design and dither patterns website for MOSFIRE. So this is the ABBA dither pattern. So it will go up and down the slit and by 1.5 arcsecond increments. So you have the A position and the B position. And that way you can image different parts of the sky with respect to the position of your star, so that when you subtract the two, the star is not in the same position in the images, so that you subtract the sky from the exposures, but you do not subtract the stars from each image, each concurrent image itself. So when you subtract the two, you subtract out all the sky, but the signal from the star remains with the sky subtracted. So it makes a much cleaner signal. But right now, I think we're on B position right now. So this is exposure number 2. So when this exposure finishes, we'll subtract an A dither from a B dither. We'll have 2 different positions of the star with respect to the pixel coordinates, so that when we subtract the A minus B, we'll see the trace nicely. So it looks like it just finished. And so let's look at it. So yeah, so see, there you go. So now you have the A minus B. So the A is the bright, sorry, it's the B. It's the B that is the bright trace right here. And then the A trace is this darker one right here, this black one right here, because those are negative value pixels. So if we were to draw a trace here, I'm going to look at the trace real quick. So I think we already have trace mode enabled, right? Let's see.
Yeah, a quick pointer.
We want to be on pointer, yeah. So if we do this, the signal is kind of hard to see because the signal isn't too high here. But basically this is the positive and this is the negative. So you have the positive trace here and you have the negative trace here. So this would be the B trace and this would be the A trace. And if you were to subtract A minus B, it would be flipped. This would be positive and this would be negative. And otherwise, if you don't do the subtraction, it's a lot more difficult to see. So now we're going to go to the non-subtracted version here. And you can kind of see the trace, but it's basically impossible to see. It's very hard to see. Like you have to, it's like one of those magic eye puzzle paintings where you stare at it very closely and you kind of see there's a pattern, but no, it's really hard to see. You really got to use a subtraction to see the traces. So how are we doing here? We're on exposure 3 or 4. So we're going to do K after this, right? Matthew?
Yep, we should do
Yeah,
K after this.
we're doing K after this. Okay. So let's go back and look at our game plan for tonight.
Yeah, we gotta. So where are we?
So this is the air mass chart. So we're looking at the night sky, the position of objects in the night sky in terms of the time here. This is local time here in the bottom. And the top, we have the local mean sidereal time at right here on this top x-axis. But the y-axis here is the air mass. So this is our first target, UD83. It just transited. So it just reached the point where it was at the lowest air mass in the night sky. And we're past that hump there. So now it's going to lower air mass. So we're trying to finish it up before it gets too low. Within the next target right here, I'm thinking maybe actually we might do the near Earth object. Just give that a crack. I think we're going to need like a solid 2.5 hours to do that because it's a very complicated setup and we're going to be doing imaging. But if we have time after that, we'll try to do the 2007 RG. But certainly in the last bit, we'll dedicate to doing
the 2007 RG one is pretty bright. We can do it in pretty rapid time here, I think. So we have 25 more minutes on this target, basically.
Okay. So we're doing the Ks now. After this exposure, we'll do the Ks.
Yeah, we're doing Ks. K is going to take no more than it's 25 minutes, I think. So.
Yeah, okay. So that will put us from here to here. Yeah. Yeah, so these it sounds like these take about an hour. So then that will put us over here if we do the 2007 RG. Okay, so let's do that one, but we might not be able to get to this last one, 2015 WX379. Because it's going to take a minute to do the near Earth asteroid imaging properly, because we have a very complicated setup tonight for doing imaging. We think we can get it to work. It's just complicated.
Is the imaging setup different than you've used before?
Oh yes. So let's look at the detector here. So this is in spectrograph mode. So let's see if I can load one of the earlier exposures.
And we're stuck in spectrograph mode. So we have to do some very janky tricks here to really get any kind of imaging.
Yeah, so I don't remember the exact file name, but I'm just going to go backwards and up. So this is like 8 every 8, 8, 8. So we were doing some imaging earlier. I think maybe 77 might be an image. Yeah, so this is the image right here. So this is what the image. So we're in spectrograph mode. We're looking at things through the slit. But in imaging mode, we can see a picture of the slit itself. So this is what it looks like. So we have the slit. This diagonal line right here. I'm going to go zoom fit full. Let's see how much time. Oh yeah, I'm going to have to explain this very quickly. Yeah, so this is what it looks like in imaging. So this is a spectrographic slit right here. But this little postage stamp area here, this little rhomboidal looking thing right here, this is where this is all the real estate we have to do our imaging. This little tiny strip here. It's not impossible. It's difficult, but it's not impossible. So we have a special routine set up that will take care of that. So
I see.
So we just finished a B. So if we do B minus B, we're not. Oh, we still see something.
Because it's B minus A.
So this is B minus A. So its current depth of position is A. Oh yeah, because this is the last one. So if this is the last exposure.
Yeah, we're moving to K.
Okay. So all right. Very good. Okay. So that was the last A in the ABBA. So this is A minus B. Yeah. Yeah. So we're good.
Yeah. So it says the wall time for K overall is going to be 27 minutes and
Yeah,
20.
it's under half an hour, so that's pretty good. So yeah, if we can like tighten up the acquisition, because
Yeah.
we're getting better at it now, right? We're getting better at the acquisition. We can do the standard and we can do the science. We can, yeah, if we can do it like under an hour, that would be great. Yeah, there's some overheads from the acquisition. The acquisition is very complicated, but we're now getting good at
We're
it.
at where 621, right? Or... Oh,
621. Yeah, 621. So this is bottom time here is local time. Top time is local mean sidereal time. But I'm going to change that to UT time.
yeah,
So we're at
there
621. I like the local mean sidereal time because that kind of tells us where things are in the sky by looking at their hour angle. But we can put it in local
yeah,
time.
switch it to UT just for my
That
sake.
makes,
Thank
yeah,
you.
makes it easier to see because we have many different ways of keeping track of time in astronomy. So local, you have your local time, which is the local time, but we also kind of have universal time, which is time basically in Greenwich, England. And that's kind of like the world clock, let's say. So you don't have to deal with the different time zones when keeping track of time. So whenever we have an ephemeris, whenever we look at the time, whenever we look up the position for an object, it's the object's position is listed in terms of UT time. So for example, this is the position of this object right here at exactly 0 hour on the 12th of February UT time. But the actual UT time is right now, it's 6 o'clock. But when we make our target lists, we list out the positions of the object in terms of, so we have the name here, but then we have the UT time that position corresponds to, because these are all moving solar system targets. They don't stay stationary. So we have to, their positions, their RA and DEC positions change throughout the night. So we have to look up the position of the RA and DEC as a function of time, and it's always in UT time.
I see that you use the ephemeris data from the Minor Planet Center. It seems like quite a bit.
Yeah, so this is from the so I use both the Jet Propulsion Lab and I use both the Minor Planet Center. So the MPC is nice because you can quickly look up the approximate locations of a bunch of objects all at once. The JPL has more precision. They have a better way of tracking the ways that the planets affect the orbits of asteroids compared to my Planet Center, but you can only do one object at a time, so it's not as convenient to use. So we use a computer program that generates this target list, but for just looking for observing in our browsers, we like to use the Minor Planet Center. So we have Laura May here. Welcome back.
Thank you.
So we have to put the lays on, and we're not allowed to put the lays on ourselves. It's a Hawaiian tradition.
That's right.
You have to have someone else put the lay on for you.
That's right. That's right.
So let's see
I'm
here.
so glad the lays have held up from yesterday.
They're beautiful. Thank you so much, Eureka.
So
My
here,
pleasure.
I'll put yours on first.
Okay.
Yeah, you have to. It's bad luck to put it on yourself. Okay, thank you. All right.
All right.
Yeah, so we're doing our we have the lays on for observing here in Hawaii. And Jamaica got these for us as presents.
Yes. Oh, I'm so happy. And Matthew, I hope you can at least wear your lay for one day when you.
Yeah, this looks like this one will be done in about 10 minutes, 10-15 minutes. And then we'll have Laura May's turn to drive the telescope. She will do the acquisition for the next target. Do you want to do that? Do you want to do so she wants to have a crack at driving the telescope. She was doing it earlier. She was taking our flats and helping with the acquisition for this object. So we'll work as a team here. We give everyone right now. Matthew's driving the telescope. We're taking turns here. And then when it comes time to do the near Earth asteroid, I'll drive the telescope.
Is our star list correct now?
It is correct. We got it all in. So I have this is sort of a list view of the game plan for tonight. So this is UD63. So we got H and K. So this is the same one we observed last night, Matthew. You just wanted to get more H and K?
Yeah, we didn't get K of it, I believe, last time. We just got
All right,
YJH.
so I have YJH. Yeah. So
Yeah,
we'll
now we
get
have the full JHK.
Yeah. So let's check on those sky conditions tonight, because we need very clear sky conditions for our imaging technique. Our imaging technique is very complicated tonight. So we need photometric conditions. So we also have something called the sky probe. The sky probe is an indication of the atmospheric attenuation caused by clouds. It's a very important thing that astronomers need to take note of. So this is like 3 different zoomed in versions. So this is a version of the atmospheric attenuation zoomed out of scale between 0 and 1 magnitude. This is a version of that, another version zoomed in between 0 and 0.2, and this is another version zoomed in even more between 0 and 0.01. So in the most zoomed in version here, we can see that the atmospheric scatter is about between 0.01 and 0.02 magnitude. So that's very small. So when you're doing your photometry, the scatter and the photometry that you're getting from the differences in the atmospheric attenuation over time is on the order of 0.01 to 0.02. Now, if you're doing in-field calibration, that you don't really have to worry about that as much. If you're using if you have a wide field camera, so MOSFIRE normally has a 6 arc-minute wide field camera, you're going to get lots of background stars. You can do calibration with the in-field stars, and that you don't have to worry about that, because the atmospheric attenuation is taken into account with every exposure you're taking. But if you're doing separate standard star and science target observations, the attenuation between those 2 different observations will affect your photometry. So what you need is, quote, photometric conditions. That is, conditions where the scatter is very, very small. So in this case, it's on the order of 0.01 and 0.02 magnitudes. So that's very good. This is considered to be pretty much photometric conditions right now. Now I'm just looking at these the sky maps here, just to make sure there's no clouds coming our way, because if there were clouds coming away, we would want to make note of that as an indicator of roughly we expect that there to be considerable variations in the attenuation caused by the atmosphere. So let's see here. We're also going to check on the satellite. That's another thing you keep track of. You look at the satellite images. So this is like a zoomed in picture in the infrared of Hawaii. So we're going to turn on the animation here. So we're going to do the from the last 3 hours. So this is Zulu time, which is also known as UTC time. So I'm gonna stop the movie here. Advance 1. So we have 6. This is what the current map looks like right here. We don't really see there. You don't really see. You see some orthographic stuff here, some orthographic clouds, but really the really bad clouds that were around earlier went away like as of an hour ago. Another thing we can look at here, we can look at the water vapor maps. So I'm going to go here, and we want to have lower. This is kind of hard to see. Yeah, these are actually kind of hard to tell, but this is from the upper atmosphere. This would be like upper atmospheric clouds. So this is still the cloud map, and this is now the water vapor map. So I'm going to do the last 3 hours, advance 1. So yeah, so our mountain is somewhere around here. We have a little bit of maybe water vapor moving in, but this really nasty stuff right here is going to stay out off of us for a while. So let's see.
Humidity is a bit higher than yesterday based on the Keck Met thing on the VNC. So
yeah, it's like 20% right now. So it's not bad. It's not like bad enough to where we have to close, but it's
definitely up there.
Yeah, it's around 20%. Where it starts to be concerning is when it gets above like 40, 50%. That's when usually bad stuff starts creeping in with fog and stuff. We want to avoid that. So this is the relative humidity versus time. CMHG mediogram is the most detailed one, most up-to-date one. So it looks like it's not really climbing or staying same. It's flatlining, so it's fine. Laura May brought food. It looks like she got some good stuff. But what did you get? Oh, wow, that looks really good. It smells really good. Oh, thank you. I
Are
probably
there,
won't-
is
I
there
won't be
any
fine.
effects from, because Kilauea just started, what is 9th or 10th eruptive episode earlier?
Yeah, we went and
today?
saw that. We went and saw that today. We
Oh,
went
you
and saw-
did?
Yeah, we saw the eruption. That was really cool.
Yes, it
It was
is.
the lay
So-
that brought us luck, I think.
Yeah, we were very lucky. It started around like 11 o'clock today, so we were very lucky. Sorry, I'm signing into my Zoom here, so it's not this annoying pop-up every 5 minutes. Let's see if I click on that. It's still the annoying pop-up. Okay, so if I go here and I go to participants, how do I get the videos to show? Let's see. Oh, there you go. Now I can see y'all face to face. Yes.
Yeah.
So yeah, Mauna Kea is going. Let's see if I can find that on the web real quick.
I just dropped the link in the chat.
Okay. Let's see if I can pull that up.
Did you see any Pele's hair?
Oh,
No, we did
No.
not see, but maybe if we go back later.
we heard the
tomorrow
roar.
or-
Yeah, we heard the roar.
Wow, yeah.
Yeah, we got pretty close, went to a part of the rim where you could get pretty close to where the lava was coming out. It sounded like ocean waves. And it was pretty wild. Yeah, exactly. Laura May, do you have a way to like text me the video that you took and I can like show them? Or maybe
You're not on an iPhone, are you?
I am on iPhone, but
I don't seem to be able to.
Wow.
yeah, actually, you know what? If you airdrop it to me, let's see. If I go to airdrop right here, and yeah, if you see, oh yeah, see MacBook Pro de Laura, do you have a way to airdrop me the video?
I'll try.
So yeah, Laura May got some.
Which viewpoint did you want?
The one showing the most lava. Maybe both. Maybe the close up, the far away one, like where we got the far away view. When we were very close, we could see little bits of lava jumping over the ridge. It's really cool. It's got a very unusual color. It's hard to describe, and the video doesn't capture it very well, unfortunately.
Yeah.
But it's this very weird, like it's like pale orange looking color, and then when it comes out and it's cooling off, it starts to become like red, dark red, and then like a reddish brown. It's very interesting.
Are you on AirDrop?
Let me get on.
Bolin MacBook?
That's me. Let's see. I don't do airdrops very often, so I'm curious to see how that works. Is it sending it to me?
Yeah, but it's a video. So it's
It might take a little while.
So, Jamaica, I'm sorry to be eating on camera, but because we did volcano stuff, I did not have any time to eat.
Yeah,
today.
we're very hungry. Yeah, we basically like we saw it in the news. Oh my gosh, eruption! Like, and we ran in the car, ran to the car, and started driving off.
Yeah, no, that's exactly what you do. Absolutely. So were you parked over at the lookout between like by the Jaguar Museum, like before that, where
the big lookout that's kind of
Yeah.
far off from that very well, we did the one that's next to sulfur something.
oh
steam
yeah,
vents.
yeah,
Yeah, the steam
There was
vents.
the steam vents.
Exactly.
the steam vents are right there.
And then we went further all the way to the end just to kind of see that other view from the backside. I'll
Past
admit, I'm very privileged. I have done so.
The close up one, like when we were up on the ridge, you could see the lava hopping up the ridge. So this is what we saw earlier.
Whoa. Oh,
Yeah,
that's better than what I saw a few weeks ago.
Yeah, it was pretty wild
Yeah,
because I'd never seen lava before.
yeah, that was the thing. That's actually
Oh, your first time! How exciting!
After fire,
Ha ha ha
literally.
ha! Fire baptism.
At night, it's really cool too, but it's more of a glow.
So let's check on the data again real quick. So is this K?
Yeah.
Matt?
Yeah, the trace is pretty faint, but that's K-band for you.
I mean, I'd say that's pretty good.
Yeah.
What's the relative brightness between this target and the next target? Let's see. You got this.
Next target is 0.4 mag fainter, brighter, I believe. Sorry.
Okay, so it might be a little bit better.
Yeah.
Okay, great. So let's see here. Let's see if I can go here. Let's look at the other view. The other view was really cool too. So this is where we got a lot closer to it. And you can see little bits of lava jumping over the edge. So this is like right behind it. And you could hear the roar. It sounded like ocean waves.
Wow.
Yeah, it was pretty magnificent. And you would when there would be a huge gush, it would sound like you could hear it pick up in volume. Let's see if I can like fast forward through it a little bit. There we go. Whoa, yeah, you can see it leaping over there.
Yeah.
Yeah, it hangs in the air. It just hangs out in the air and cools and goes from like
Wow.
bright, like kind of like a pale. Yeah, you can see it right there.
Yeah.
Yeah.
Nice because Hawaii caters to so many sciences. It's one of the cool things about coming here.
Yeah, look at that.
You know, there's amazing weather stuff, there's astronomy, there's geology,
Yeah,
there's
oceanography.
Oceanography.
There's actually a volcanology conference happening right now.
Yeah,
Oh,
a
wow.
friend of mine told me that one of her friends, she's a geologist, and she was like, "Oh yeah, my friend is at the conference."
Wow.
Yes. And this
bet
is
those
the
people are
reasons
happy.
why.
Yeah, Fire's a Pele. You know, she wanted to show off for the volcanologist.
That's right.
That's exactly what I was thinking. Wow. Well, clearly I'm gonna have to go down there tomorrow if it's still happening.
Clearly.
Oh yeah, I highly recommend it. It was
Yes.
really cool.
Thank you for sharing these incredible videos.
Yeah, sorry about that. A little bit off topic of astronomy, but you know,
There are volcanoes in space.
yeah, there are space volcanoes.
Yes.
Can
exactly.
anyone here of our guests tell us which body in the solar system has the most volcanoes?
It's not Earth.
It's not Earth.
You can put your answers in the chat. Which body in the
right.
solar system has the most volcano? Yes. Oh, Jim, you're right. You're right. Let me put this.
Do we have any answers?
Let's see. Well, first, Jim has a comment, which is science is science. This is great. Yes, I agree, Jim. Let's see. Any takers for the object in the solar system that's the most volcanically active?
It is a planet. It is a planet. There's a moon that's also very volcanically
There
active.
is. So
And
I was thinking the moon, but that's not what you're not thinking Io. No.
And there are also comets that are volcanically active with cryovolcanism.
Yeah.
It's pretty awesome.
Okay, I think you're gonna have to tell us.
Okay, so the answer is Venus. Venus has, I think, over 1,000 volcanoes. I thought briefly that it was Io, but Io has, I think, a little fewer, but we recently had a news on how they were showing that basically it's not one magma chamber on Io, it's lots of different ones.
Oh wow.
But Venus has volcanoes also that are active right now. It's pretty incredible. And there's a lot of, you can study them to understand part of the greenhouse effect there and what's replenishing Venus's, if Venus's atmosphere is being replenished in CO2 and other things, because its atmosphere is not being stripped by the solar wind, unlike Mars. So it's pretty interesting stuff. So if any of you want to study volcanoes on another planet, there are a lot of people who do that.
Oh, yeah. By the way, I have a quick question for you, Matthew. Is this so this
A minus A.
This is A minus A because we're on the second one, which is the B, right? So
Yeah, we're taking a B right now.
okay.
Yep. So we have 2.5 more exposures left. Then very quickly slew over to our standard, and then take another one of these centaurs.
This is a very good falafel sandwich.
Jamika, do you know anything about the Solar Observatory on Mauna Loa?
Do what now? What about it?
Do you know anything about it? Because I know it shut some years ago because they had the eruption, but they were meant to reopen last year. And I checked on their website because they keep saying, "Oh yeah, we're going to reopen now" or something. But I haven't found any news in the past year, and it's past their reopening. But I check very often the Gong network, which is the network of solar telescopes, and it keeps, and it says the last image from them was 800 days ago or something. And they had said they were going to reopen around the eclipse last year, and so I'm surprised that there's been no news about them.
I sure don't know, Laura May. I sure don't. If I hear anything, I'll certainly let you know.
Maybe with DKI, I don't know, they've stopped operations, or I'm not sure.
Yeah, with DKIS, but I would imagine, that they would continue if they have a
Yeah.
facility that works.
It actually surprised me that solar astronomy is not bigger in Hawaii. So the visitor center at Mauna Kea no longer has that solar telescope. Apparently it fell over. They were telling me that the star parties there are complete chaos because a lot of people are not necessarily used to telescopes. And so that scope apparently fell over and everything's broken. And, and I was like, man, you have the most amazing skies here for solar astronomy too. So I really wish that, there was more of that, and DKist is here, and yeah.
Yeah. Yeah, that's so
Some of
true.
my colleagues are sending me images right now, earlier from our celostat at our observatory. 'Cause I'm, like,
Really?
meeting the sunspots.
Well, I'm sorry I couldn't get that set up for you all to visit DKIS
Oh,
this
no,
time.
it's all good.
No,
Yeah,
that's totally
they're busy
fine.
right now, so totally get it.
Next
It's an
time.
occasion to come back. Hey, we got lava. I feel like
Yeah, it's
we
just
got lava,
yeah.
so I can't really complain about anything.
Okay,
it's
good.
incredible. Like
Good,
I was
good.
here a couple of years ago during Halloween, and we had an earthquake, which was cool. But like 2 weeks after I left, they had like this huge eruption on Mauna Loa. I was like, oh no.
Oh, it was incredible. Incredible. Incredible.
Yeah, you could see it from Halepahaku, I think, pretty well. It was
Oh, yeah.
pretty lit up.
Oh yeah, I mean, we were parked on the side of Saddle Road for miles and miles. Just, I mean, it was an incredible, so incredible. Yeah. Oh, Laura May, Jim, who, so excited that Jim is here. Jim is a fan from All Space Considered.
No
And
way!
yes, and he actually,
Hello, Jim.
yes,
Joining us. We need to talk.
this is how he found out about Shadow the Scientist, is from All Space Considered.
That's awesome. Oh, yay. Well, I will, in fact, I'm sure maybe my boss is like, when is she coming back? Because we are filming another episode next week. We have a very exciting episode for AAS. So we're going to cover all the important news of AAS. We're trying to make a fun tier list episode. With like,
You want to spot?
no, right now? Oh, no, it's
Yeah,
fine.
you
It's
want-
fine.
you want
It's
to be
fine.
closer to the
It's fine.
camera?
It's fine. It's fine.
Cool.
So yeah, and then we have Andrea Getz, Nobel Prize winner from UCLA,
Oh,
who will be coming on the episode in March.
Oh, wow.
Andrea Gibbs, oh my gosh, I love
April.
her.
In April, we are doing a 90th anniversary for the anniversary of the observatory. We're doing a time travel episode where we're going to cover astronomy news from 1934-35. We're actually trying to get costumes. It's total chaos.
Wow.
We were going to do it in January, and obviously the fires happened. And so we're hopeful that this episode will draw like a lot of interest, because it's so fun to think about stuff that we knew or didn't know 90 years ago when the observatory had just opened. So thank you, Jim. I hope you either come visit us or watch it, because it's going to be super fun. And we'll, if you're online, please send us questions and things, because yeah, that's good fun.
Well, I will definitely be joining online, and Jim just also shared that Raja, who's the founder of Shadow the Scientist, was
Oh,
a
wow.
guest on All Space Considered some years ago.
Yeah.
Wow.
And Raja
Yeah.
came to visit us, as you may know. I met him, I think last year, the year prior. He came to visit us at the observatory because I guess my semi-boss, Dr. Reitzel, was his student. I think.
That's right.
Something like
That's
that.
right.
Yeah.
Yes.
Wow.
It's all interconnected in the sciences.
Oh, wow.
Exposure,
Yes.
sleep.
I will be joining. Jim says he watches every month, haven't been in person since before the pandemic. So
Oh.
Oh,
Yeah.
why not? Well, yeah, fair enough. A lot of people don't want to show up. And also, we used to do it on first Fridays, and now it's third Thursdays. We're also going to hopefully roll out a podcast version. So we have a lot of stuff. But yeah, thank you so much for watching, because we're kind of a small show that's really being done kind of in our free time, and we're just cobbling a lot of stuff together. And we don't have the means of a large production, but I think everyone's really passionate and dedicated. So we really appreciate people listening in and sharing, and yeah, it's really cool. Thank you for supporting.
absolutely. Is it do you promote it on social media? Because if so, we'll
Kind of, you know,
certainly
the
share it.
observatory, we're a little bit under-resourced, so we don't have a social media person. We do have a wonderful person called Pixie who does some of the, you know, I've sent in images and things, but a lot of people at the observatory have lots of different roles, so we all kind of do lots of different things. So we try to promote it. In fact, we sent her some stuff to send out about the AAS stories that we'll cover. And hopefully we can cover YR4, one of our potential targets for tonight, because I know there's a lot of interest in this new killer asteroid.
Oh, yeah. Maybe we should do that one next so we can show the audience. Y'all. We could give that a try. Show the audience the killer asteroid with the with the Keck telescope.
Scare people. It's
No,
not even
no,
Halloween.
no. Don't scare. Don't be scared.
Right, so it looks like y'all have things under control. If I head out and, are you
What do you think?
around for,
Well, I don't know. We don't want to like capture you here, but it might be helpful when we do the imaging later. An extra set of eyes. And,
Can we contact you later? Potentially? Yeah,
I'm on call.
awesome.
Here, I'll put my phone number.
okay.
Awesome, thank you.
So that you can contact me whenever you need it. Okay, bother me. I'll also be online for the changeover second half night. of the other team.
Oh, right.
Awesome, thank you so much.
All right. So we're almost done with this one.
Yeah.
So let's see. We have about how much time do we have left on Shadow of the Scientist?
We have about 11 minutes.
Okay.
But
And the
we-
time it'll take us to move and acquire, I doubt what we'd
it's worth staying on just to get to see this
What is it? 1.1
potential
MS?
asteroid.
Yeah. So right now, well, let's see.
I mean, can we avoid I mean, I know you want to do it for 2.5 hours, but could we just try doing it for like hour and a half and then get back to the centaurs, or do you just want to?
Well, you wanna do the Centaur real quick, Matthew?
I mean, it's nothing's gonna be particularly quick. We should make a decision because we just finished our last image here. So
All
do you
right.
want to
Well,
move to standard?
let's try and do YR4. Yeah. So we're going to be doing this in imaging mode.
Thank you. It's
Thank
awesome
you,
meeting
Leo. I'm going to put this in quick dark mode so we can.
I already did.
Okay. Thank you. So the standard star for this one is 2 mass. All right. Okay. Thank you. So Tony, we are ready to go to our standard, the standard target. This one should be north up and east to the left. Yeah, it might be better to do this one now in case the cloudiness, some clouds roll in. It looks like there might be some clouds rolling in a little bit later, so it's probably better to do this one because we will be most dependent on the photometric quality of the sky for this target.
I'm just worried that you're not gonna actually like what are you trying to get out of it? Why J bend?
Yeah, we'll try getting it in Y first. That's like the highest throughput, but ideally it would be nice to get the near infrared colors.
I mean, you're just not gonna get H bend or K bend. You can get a Y minus J. I'm pretty confident, but H
Yeah.
and K is just yours. You're gonna be staring at noise.
K is very sensitive actually, but we will see. Let's give Y and J a try. So let's see here.
But
So we-
what are you actually getting out of this? So if you have the say GRIs, do
Yeah,
you
so,
actually
so we're
get a
getting,
good?
getting the colors of it in the near infrared. So that is going to give us some indication of the type of silicate, the amount of silicate absorption. There is a silicate absorption band at 1 micron, and by measuring the Y, J, H, and K colors, we can get some. And there's also one at 2 microns as well. We can test the amount of absorption in the spectrum of this object, even though it's a super coarse spectrophotometry. We can test the amount of silicate absorption in the spectrum of this object.
I'm just not sure you're going to get the signal to noise that you need to get, say, 20%, even like a 20% absorption in Y.
So with a magnitude 23 object, which this object is in Y, we can reach a signal noise of 20 in a 1500 second equivalent exposure time.
Yeah.
Matthew, while everything is slewing right now, could you quickly just explain what has happened up to this point? We have a participant who had network issues and just joined us and wanted to just catch up.
Yeah, so we've been collecting spectra in the infrared of centaurs, which are asteroids on orbits that bring them between Jupiter and Neptune. So sort of traverse between the giant planets on very unstable orbits, and they're sourced from the Kuiper belt, which are these asteroids in the farthest reaches of the solar system. And we're trying to test if they have any water ice or not, because as we've discovered, a lot of these asteroids, they sort of fall into a class where either they're very rich in organics and they have these features from, or absorption features from methanol, whereas others have rich water ice, and sort of trying to get more population statistics on whether an object falls into the first category or the second category. And so we just got a spectrum of one of these objects in H and K band, which is what we need in order to determine whether it has the water ice absorption at 2 microns and whether it has a methanol absorption potentially at 2.2 microns.
Thank you, Matthew.
So I'm going to make a new command here that is just for placement of the object in the postage stamp region.
I have your standard star at MOSFIRE for your origin.
Okay, all right, we're gonna move it into the postage stamp now.
Okay.
Here we go, postage stamp time. So I am going to just do one coad of 30 seconds here because this thing is. Sorry, Yale. Dark spectroscopy mode is a mode that we use when we're slewing the telescope. We basically put a dark filter in front of the detector, so that as the telescope is slewing, if we accidentally pass within or over some super bright star, we don't have to worry about it.
Exposure complete.
All right, well, there's the standard star. So now I'm going to create a special move mode for it. So we want to put it
minus 0.3, I'd say.
We want it to wind up around here. We want it to say put it at 994/1985. So this would be 994/1985. This is where we want it to wind up at. And where it currently is located, I prefer to use my Mac's finer control with the touchpad here. Let's see if I can get a little bit more precise. I'm going to go to, yeah, we're already at min-max scale. So let's see. Yeah, we'll call that good. 1982, 1994. 982, sorry.
Yeah, 982, 1990.
982, 1994. 982, 1994. All right, good. So this is the special location for imaging. So I'm going to write that down here. Write that down.
Want me to start taking the images?
No, let me do this, Matthew.
Okay.
Four. So the special location is 1980, 994, 1985. 1982, 1984, 1994, 1980. Okay, good. So, all right, so now we're going to take another image, another test image. And now this is where it's going to get interesting because I have to set up a dither pattern so that this object wanders up and down this little push step right here. We want 5 unique positions in order to get the least amount of redundancy in the sky levels. It's for sky removal. We want the least amount of redundancy between images to facilitate better sky removal. Okay, so this is going to show us.
Exposure complete.
All right, so that's about what I expected. I'm going to put the color here to, I prefer gray. Tell. So use my max here. Yeah, so you can see the positive and negative. So yes. Okay, so yeah, so that's about, I think that's about right. Maybe we will move it just a little bit less on the y-axis, on the x-axis. So instead of 1994, we'll do 1993.
Oh, we can't see the image. There's your ephemeris data.
Oh, my
Yeah.
ephemeris data. Oh my gosh, I'm so sorry.
No worries. Thank you.
So yeah, we will walk it back. In the final version of this special script, we will walk it back just a little bit. So it will be at 993 instead of 994. But for the purpose of taking the standard, I think we'll work with this. So now I have to use a special mode. We're going to go to the special configuration mode that is called a slit nod. So I'm going to edit the parameters here. So the nod positions that we are going to, the slit width, the full slit width right here is technically 14 arc seconds, but we're going to be safe here. We're going to use a slit length. Let's say, let's be safe here and say 12 arc seconds. So this distance between here and here, I'm going to go to region, shape, ruler. This is this position between here and here. It's in degrees units now. I'm going to make it arc seconds. It's about 20 arc seconds. Actually, it's not as bad as I thought it was. Okay. So the distance between here and here is 20 arc seconds. But just to be safe, I'm going to say it's a slit length of 15 arc seconds. And then we're going to take 5 positions. Actually, just to be safe, I'm feeling better if we take 12. And we'll do 14. Okay, so we have 5 nod positions and along a slit length of 14 arc seconds. So we are going to hit go. So what should happen is that this star should dither up and down the slit. I'll show the cartoon.
It's very well centered. Hold on. Postage stamp.
Yeah, thank you. So this is called a slit nod pattern. So the first exposure is going to go up to here. It's going to go up what looks like to be about 3.4 arc seconds. And then it will go down to here. The first exposure is going to be right here in the middle. but it's going to go up. The second exposure is going to be 3.4 arc seconds north of that, and then or greater in y direction than that. And then the third exposure is going to be exactly opposite of that, 1.7 arc seconds below that, and then it's going to go to 4. It's
Bryce,
near-
you've done too long, I think, exposure times. These 30-second ones are too long.
Should we abort after frame?
You're close to
okay.
saturation.
Let's let it. This is a test of the slip now. Let's let it go
Okay.
because
I mean, have it do one more, and then I would abort after this frame just to make sure it jumped, but I'll abort after this.
yeah, let's let it go through. We just want to make sure it works.
I mean, if
Because if
one
we-
works, I imagine the rest of them are going to work.
If we stop right in the middle of its process, then it might not start again right in the middle. So I prefer to just let it go through.
Okay.
And then we have to reacquire and recenter and all that. But yeah, it is doing what we think it is doing what we think it's supposed to do. So yeah, technically it is a little bit non-linear here, but the non-linearity is not as bad as we think. So maybe we can actually just keep these and go along with it.
It's here.
Here, wait, here. Let me control it, please. Matthew.
Exposure complete.
Having multiple inputs is makes it difficult. Let's see. Yeah, so it is a little high. It's a little bit north of 30,000.
Can we see that image, Bryce?
Sorry about that.
Exposure complete.
So it looks like it's staying like within the confines of this postage stamp. So I would call this a success. So it's right now it's doing the fourth one. So where we are in the slip pattern is right here. It's upside down, but this is actually numbered the fourth one, and the fifth one should be somewhere up at the top.
Exposure.
Yep, there it is. So this was a successful test. Yeah, just to be safe, yeah, we'll do a 15-second eye time here. We'll do this all over again. We'll see it jump around. So I'd say this is this as far as testing out the imaging slit nod capabilities of this weird mode of the instrument that we're using it in. I'd say it's a success so far. Let's check our yeah, it's
Exposure complete.
let's see, let's check the guide probe. I mean the elixir sky probe. Yeah, so it looks like atmospheric scatter is pretty small. Looks like the sky is still clear. I don't see any clouds moving overhead, so it looks like we're pretty good.
Exposure.
Looks like what
complete.
clouds there were have dissipated or passing. Maybe some very slight clouds with very upper atmosphere, but they're not having a significant effect on the attenuation. So let's see. There we go.
Exposure complete.
So I would call this good. So now we're going to do H and Y, J, H, and K. We're going to get standard observations that are standard in all 4 filters. And the reason why you do the standard first, you always
Exposure
do
complete.
standards when you're doing spectroscopy or you're doing imaging that requires a standard. Always take your standard first, because no matter how awesome the data of your science target are, no matter how great and how much integration time you spend on it, it's worthless if you don't get a standard. So if you're in like a stormy condition where you might have to close, if you spend all your time taking the science observations first, and then you have to close the telescope, let's say it starts raining before you can take your standard, then those data are very, very difficult to reduce. So always take the standard first.
It sounds like you learned that from experience.
Well, someone no, it was actually I had a very good teacher, a very good instructor on how to take standards and science targets with spectroscopy by the name of Melissa Graham. She's at the University of Washington. She's a scientist at the University of Washington, and we were doing a lot of follow-up of supernova targets. So I'm gonna like eyeball this and say, I think maybe 10 seconds here. Well, actually, for Y band, for J band, the maximum recommended exposure time is 10 seconds. So I think we're
J-band, you should do 4 seconds, 5 seconds, maybe 5, not more.
we're gonna try 10 seconds here.
You're definitely gonna get close to saturation. Try 8.
You want to try 8, what Matthew suggested?
No, I'm gonna try 10. We'll try 10. This is just gonna be a test.
What did you end up, you decreased Y band from 30, right? What did you end up decreasing it to?
We did
Remember?
15.
15?
Did you end up doing 15?
Mhm.
Yeah, I think so in the end, yeah.
Or are you just doing a single? Did you only do a single 15, or are you doing both?
This is we had 5. So this is so this is a little high maybe because we're starting to see that the hat. So whenever you see this little structure right here, that means the center pixel is starting to become saturated. So we want to decrease it a little bit. Yeah, we'll go to 5. All right, so now we're going to go to our line slip nod. So it's 5 positions, 14 arc seconds. So we're going to hit go.
Exposure complete.
We didn't really see that little hat part you were talking about,
Oh,
Bryce.
sorry about that. Yeah, it's hard for
No,
me to manage the
was on the
all
graph.
the VNC viewers.
I appreciate all the effort that it takes to allow us to really be so immersed in everything going on. Thank you.
Oh no, it's great. It's my pleasure. So it looks like, yeah, so before there was this hat. So yeah, we're still seeing kind of a hat here. Maybe
Exposure complete.
What's the minimum time on integration for that?
maybe to be safe, we'll lower it to 2 seconds, the
yeah.
minimum time.
Exposure
Yeah,
complete.
it's the telescope is too powerful. So it's maybe a little bit of a hat, maybe not. So there is this hat, though I call it the witch's hat, but sometimes it turns to a cowboy hat where it gets flat at the top.
Exposure
So-
Kind of,
When the witch's hat turns into a cowboy hat, that means you're saturating. So you don't want the cowboy hat. So we'll do this again. Yeah, sorry, the telescope is too powerful.
exposure complete.
I'm sure that's not a bad problem to have.
Well, for getting cals, it is tough. It is difficult. It is difficult because most of the
Exposure
calibrator stars, well-known, well-characterized calibrator stars, are made for either spectroscopy or observations on much smaller telescopes. Even with the shortest.
Exposure
Oh, what's happening
complete.
here? What happened?
where'd it go? That's weird.
Matthew, did you touch anything?
Nope.
Exposure complete.
So I have to find the DS9 in here.
Exposure
I think it's under utilities, no?
Let's see, I didn't see it. So we have here, it just disappeared. While I was drawing a trace, it just disappeared. So hold on, hey, don't touch it, please. Control menu, utilities. Yeah, I don't see DS9 in here. And we might have to call. Do you think you
You want
can
me to
call?
call
Yeah,
Leo?
can you please call Leo? Yeah, some weird Linux thing happened. Definitely don't want to do that. You definitely do not want to click that button.
I believe you can try typing in DP into the
Hold on, we're gonna call Leo here.
I think I can't. Oh, there is a phone here. Okay. So the number is 80.
Oh, yeah, it's doing the weird thing. You have to like press 9 or something.
Yeah, to get out. Yeah. So 808-6300-809.
I'm gonna change this to H. So we're gonna do minimum here. And I'm just gonna do a slit notch. So we're still collecting photons while we're trying to figure out how to get DS9 to pop up again.
I think
Hey,
that
Leo. Hi, Leo. How you doing? So where are the DS9 window kind of like disappeared mysteriously while we were trying to do something on it. Do you know how to make it pop up again? Okay. So I'm on MOSFIRE control 2, and I see there's MOSFIRE control menu in the right click menu. Okay. DS9, restart DS. All righty. So let's see. Let's check. We're gonna check to see if this is saturated or not. We were taking some H-band imaging of standard star target. Here we go. Let's see, zoom, bit to frame. Is everyone able to see this on Shadow the Scientist?
Yes, we definitely are.
All right, yeah, this sometimes happens. Sorry. So scale, min max. Okay, I think I see the source. Got shimmy it up a little bit, and then
yeah, you're not saturated. You're fine.
shape. We're gonna go to projection, and yeah, this looks good. Okay, so we'll call it H. Yeah, thank you, Leo. Sorry to bother you at home. All right. Well, I appreciate it. I hope we don't have to call you again. I don't want to have to bother you again, but thank you for saving us here. All right. Well, thank you so much. I'll leave you alone now and have a good rest of the evening. Okay. All right. Cool. All right. All right. Talk to you soon, maybe. Take care. Bye. Yeah, sorry about that. We had to call tech support, the telescope tech support. that was Leo. She was here earlier, and she's a support astronomer. So she's someone with a PhD, very experienced in science, and is also the master of the instrument here, who's kind of guiding us. So it looks like we have pretty good try here. So we're going to do this in K now. So we're just going to keep it at 2 seconds. 2-second exposures in K. We're changing it to K band. Here's the first image. It's downloading.
Exposure complete.
All right. Okay, there we go. I had to adjust the stretch there a little bit. That made me scared. Whoa. I did it again. Okay, I figured out what's going on here. So if you are playing around with a projection while the DS9 is updating, it causes it to do that weird thing.
Exposure
Yeah,
complete.
so you go to subcomponents, you go to restart DS9 imager. Yeah. So now we know. We know now. We figured it out.
Exposure complete.
So we now know not to play around with the projection thing while an exposure is finishing up.
Yeah, it must crash it, I think.
Yeah, it causes it.
Exposure
Yep.
complete.
You know, it's the way astronomy is. You know, this is very unique software, very unique development environment. So there's all sorts of proclivities that one has to get used to. Like one thing that is very well known in astronomy is never, ever, ever press the stop button on an instrument when it's in the middle of doing something. It's kind of like, you know, Microsoft Windows going into safe mode or something. Yeah, you just don't do it. Okay, so I would call this a success. And can y'all see that? So it looks like a witch's hat. It's not a cowboy hat. So that's very good. And it looks like it's a decent amount of counts. So I think we're now going to go to the near Earth asteroid. Who is ready to see that?
We're ready. We're ready.
All right. So hello, Tony. I'm going to put in the quick dark right now, and I'm going to highlight the next target. So the time right now is 7:20 UTC. So I'm going to show them. So now I'm scrolling down the target list. I'm going to choose the RA deck for 7:20. Yeah.
Do maybe 722 by the time it tracks.
It's a good idea. So we can, you know, actually we're right next to it. So we can do 7:21. Yeah. So we are ready to slew when you are ready to go. Because we took a standard star right next to the target. So it's good. It's not much different distance for the telescope to move. So there we go. We have our target YR4 ____ 07-21. So while this is going, I'm going to look up the position of this object in.
Yeah, you can do your move to the postcard.
Oh, you're already there? Oh, wow. So before just as a double check, can you put the position of the asteroid in the Magic Q viewer? Because I want to just double check that we're on the correct field. Because the object that we're targeting is very faint, but the background stars are not, and we should be able to see them decently.
You have to stay on the guider now.
Okay. What is the field? By the way, what is the field of view of the guider?
Field of view is I don't know what it is. Mark second.
It's
So
like
look-
1.5.
Looks like there's like a scale bar here. So that's looking like maybe 4. So I would say maybe 2 arc minutes by 2 arc minutes. Something on the order of that. But let's see. So is the scale, can you adjust the scale in it? It looks like it's hard to see if there's some stars there. So this is going to be rotated because in this window right here, north is up and east is to the left. But in this window right here, it's north is to the left and east is down.
Yeah, I mean, I bet you're seeing the asterism right there because you're seeing that one bright star and then like 2 fainter ones. Right? If you rotate in your head, sort of. Or is
Yeah,
it
North is, I don't see where north is on yours. North is up on yours. Okay.
Yeah, I'm not quite sure if I can see. Okay, there we go. That looks a little better there. Yeah, it's hard to tell, but we're gonna call that good. We're gonna call that good. Let's say. Yeah, so I can see like the 3. There's like a bow here, right? There's like the 3 that like this triangle. It's kind of hard to see. Maybe the triangles because there's like 2 arc minutes by 2 arc minutes, so maybe it's something like that. Maybe these 2 stars are these 2 stars. Well, I don't know. It's not because it would be at a positive angle.
It's not very.
I don't quite. Yeah. So let's just go ahead and put the target on the in the post in the slit, and then I'll run the command to do the postcard.
Are we sure? Yeah, that's tilted, right? Because that's that pattern here.
Well, it's rotated that like that. Okay, so here we are.
Postcard.
Okay, I'm going to run the postcard command. So I'm going to go back to the terminal showing all the data stuff. So there we go. All right, that's going to put it in the postcard. So all moves from here on out should be pretty small.
Okay. I'm
Uh,
ready.
So this is going to be the science target. And we're not going to do a slit nod. We're just going to do a stare. And this is going to be a long exposure. So we're going to do 30-second eye time with 6 coads. And we will do.
In Y, you can probably do much longer exposures. You can probably do.
Yeah, I mean, this is like the recommended thing. I mean, you know, I
Did we do a quick dark?
Okay.
kind of like to keep it standardized.
What band are we in?
So we got, that's right. We got to change it to Y filter. So yeah, we're changing it to Y filter. So let's see. Let's see what we can see. So one technique here. If I do ABBA and I just keep it, yeah, we'll just do an AB. So we'll cancel it right after the second exposure. So we'll press the cancel button right after the first exposure. So we just want to do an AB.
Did we do ABBA on 2011 UD 63?
We did. But for this one, this is just for acquisition purposes. Okay, so I'm gonna hit the go button here because we are probably gonna have to do a difference here just to make sure. Because now we got, we're A, making sure it's there, and B, making sure that the
Exposure complete.
I'm not sure what that exposure complete was because that was supposed to be like a 3-minute exposure. Yeah, I'm not sure what went on there. 30-second eye time, 6 coads. So I'll board after this frame and do another go because that was weird. Sometimes this instrument acts a little finicky, but that's okay. Everyone has their quirks and quarks.
It definitely makes it interesting.
Yes, very interesting.
And we do have a few questions in the chat whenever get a chance to take a look. One is about activity on asteroids and comets, and then another one about if you work with astrobiologists when looking for organic materials in waters on sensors.
Yeah, and I see someone also put monitor the orbit of 2024 YR4. Yeah, these are all very good questions. So Laura May or Matthew, do you want to take a chance at addressing these questions?
Essentially. So why don't we work with astrobiologists? Well, I mean, there's not thousands of astrobiologists, I would say. Asteroids are not prime targets really for, well, I mean, you know, you look for there are potentially organics, Bennu, very interesting results on Bennu that have come out recently. But you know, that's not necessarily what we're doing. I think they have specific targets, you know, so they may have data or targets that are more interesting to them than this. But you know, it's a good question. I wish there were thousands of astrobiologists who could look at things, and I'm sure they would love to have data like this to see how, you know, what do asteroids look like? But I expect that, yeah, there are probably astrobiologists who work on this kind of data on occasion, and they're usually people who are very knowledgeable about geology in particular, about how, you know, the composition of everything when there's water, etc., volatiles, organic. Yeah, but you know, call an astrobiologist. We'll have to have an astrobiologist explain some of these things.
Okay, thank you, Larvae. And the other one actually kind of goes back to what you were talking about volcanoes and kind of active activities like that on asteroids and comets. How does that happen?
That's interesting. Bryce, you gave a talk on this partly yesterday.
Oh yeah, I mean,
you know, because some of them do, obviously There are comets obviously outgas more as they get closer to the sun. So a lot of the volatiles, this is why you'll see this kind of long, beautiful trail. What used to be the Coma comes from hair. In fact, that's why there's a constellation called Coma Berenices. It's the hair of Berenice, who I think was a figure in mythology. And so we call it the Coma of a comet because, or comet, in fact, because they have that long hair, and that is, as it glows closer to the sun, there is outgassing and all those volatiles that are being warmed up and creating those tails. And so asteroids, in fact, Bryce was talking yesterday about how some asteroids, I learned some very interesting things. Some of these asteroids do not have, obviously they're asteroids, they're different to comets, but they don't react quite in the same way. And so it's not necessarily going to happen at perihelion when they're closest to the sun. What was the cause of that again, Bryce? That, you know, we have this activity that can happen at, you know, perihelion or
so
other-
it's when the comets, so the sublimation rate of water ice into water gas, water vapor, increases as the closer you get to the sun. So there are asteroids which become more active the closer they are to the sun compared to when they are further from the sun. And but there are other cometary volatiles that can drive the activity of water. Activity of comets, such as carbon dioxide and carbon monoxide. But they're even more volatile, even more susceptible to. They have a greater tendency to sublimate at lower temperatures compared to water ice itself. So the distance at which water ice starts to sublimate into water vapor is about 3.5, 4.5 astronomical units, which is 3.5 times the distance from the Earth to the Sun. That's one astronomical unit is one distance between it's 1 unit of distance between the Earth and the Sun. And for water ice, that's that sublimation, the distance from which comets can be from the sun, which they start, water ice starts to sublimate on their surfaces, is about 3.5, 4.5 astronomical units. For carbon dioxide, comets with carbon dioxide ice start to sublimate a little bit further from the sun at about 13 to 15 AU. And carbon monoxide is even further out. It can start, carbon monoxide ice starts to sublimate to 150 to 200 AU from the sun.
Wow, that's surprising.
Yeah, so you can have these very distantly active comets. These comets which are very active, very far from the sun.
Check it out. I looked up just the, oh no, I guess it doesn't match anymore.
Do you want to put that in the chat window?
No, it's from a couple days ago, so it wouldn't match anymore. I had
oh.
a brief moment of thinking that
So-
it was our field. But
So Laura May was looking up the
YR4.
pictures of the YR4 asteroid.
Ooh.
Yeah, spooky.
It is muy pequeño for us. But obviously, there's so much news that's been written about it. But I do want to say regarding YR4, I don't know if Bryce already spoke about it. Its size is
Exposure
approximately similar to what would have caused the Tunguska event.
Tunguska.
Yeah, that's right. Please correct me, Matthew. Which crashed in Siberia in, I think, 1903 or somewhere around that time. And so, you know, whilst it would cause a lot of damage, it's not a civilization.
Oh, hey, there it is.
Did we find
There it is.
Yeah, there it is. Oh, yeah. Wow, we can see it. There it
Wow.
is.
Oh my gosh, we got it.
Yeah, look at that thing. I'd say it's pretty well centered.
Yeah.
I'm a little nervous to start messing about with it because I don't know where it is now.
I'd just keep hitting it with, let's just keep going. Let's get another pair of Ys.
So the thing is that I do not want it to run into this edge here, this detector edge. But I don't know where it actually is. Because it's going to be somewhere in the middle here, I think.
Can I take a
So-
screen cap on your?
Yeah, sure. So so hey, can you keep track of these numbers?
Yes.
Let's write down these numbers. Do you have
Yep.
a pen or pencil somewhere? Where's a pen or pencil?
Yes.
So I got one in my pocket.
I got it.
Okay, so can you write down 996, 1983, 387?
1983, 387.
1996, 1984. No, let's say 996.
1983.
Sorry, no. It's 996, 1983.
Okay.
Okay, and
Was there another number after 38 something? No.
so we want to move it to the special part here. So again, you have the numbers.
Yep.
996.
1983.
1983. We want to move it to the special part. 993, 1985. Yeah.
Yeah, it sounds about right.
Yeah. That was what we had.
Move it a bit left and a bit up, which should be exactly what we want.
Because we wanted to get away from that. So now what we're going to do is we're going to go into the slit. Yeah. So there's the killer asteroid. We got it.
It looks so menacing.
Okay. So now we're going to set up a slit nod. And then we are going to do, yes, we want to do Y. So let's do some Ys. Yo. Okay. So here we go, some Ys.
So
So-
6 and 30, yeah.
So the clock time here is 976 seconds. So this asteroid, which is about 15 minutes, this asteroid has a rotation period of 19.5 minutes. So that means its brightness is changing as a function of time, like a sinusoidal curve. So we want to smear that out. Usually what you would do is you would take an exposure and a filter, let's say Y. You take exposure and another filter, let's say J. You would cycle through the filters so that you would basically smear out all the light curve effects. But because we're doing this in the infrared, we have to sample the sky background pretty well in order to subtract it from each individual image. We have to do a bunch of Ys all at once. We have to do a bunch of Js all at once. We have to do a bunch of Hs all at once. And we have to do a bunch of Ks all at once. So the trick here that we're going to do is we're going to smear out the light curve in each filter individually. So this is a 15-minute sequence. So I'm thinking we probably want to do this twice so we get a 30-minute sequence so we can smear out the light curve. And so the average is out. And you take a median and then you just get the central value. So you can get the brightness of the object while minimizing the rotational variations in the object's brightness effect. So let's see here. So I think this is like most famously seen in Oumuamua. Sorry, I misspelled light curve. Light curve.
I thought you were gonna misspell Oumuamua.
Oh yeah, well
Got that.
that's a hard word to spell. But I learned pretty well how to spell it eventually. So this is what the light curve of Oumuamua looks like. It's the brightness variations change quite a lot as it was spinning around. And so it varied by, oh my gosh, 2.5 magnitudes, because it was basically like a very elongated asteroid. And so it had this very weird looking light curve. But this is not an Oumuamua. Its light curve variations are about 0.4 magnitudes, but it's enough that I can mess up your color measurements. So we want to smear that out. The rotation period of Oumuamua was 8 hours, but this one's about 19.5 minutes. So it's spinning very quickly. So we want to try to encapsulate that by taking data over 1.5. It'd be better to do 2, but Matthew here is going to send me to the gulag if I.
Hey, it's not because he's.
We got to do this right. So we're gonna do this right.
We say that because you're from Caltech, not because you're from that part.
Matthew's from where are you from, Matthew? It's Philadelphia, right?
Yeah.
Yeah. So there, yeah. So he's American.
There you go. Your origins.
But we shouldn't get political here. But I'm more likely to be sent to Guantanamo Bay.
Eureka, please cut all this out.
Oh, yeah.
I'll just edit all of this out. I'll just edit all of the past 2 minutes. All good, no worries.
You can't even blame altitude sickness.
Oh yeah. Well, there's our asteroid. I can see it. I can see it.
Beautiful.
Let's see here. Z scale. It's hard. It's hard. It's hard to get it. But I could definitely see it. Yeah, I wish I could shimmy it over a little bit more, but
I usually go to a Z scale and then A sin H, but
Z scale, A sin H, you say. Okay, let's give that a try. It's hard to see the positive.
and right there at the edge, you should be able to see it once you push
Yeah,
it.
I definitely see it. It's this thing right here, but
Yeah.
I want to show it better. Yeah, it's hard because the dynamic range of these images is not, super spot
No,
on.
no.
So I'm very hesitant to mess with this. It's very
Yeah, it
touchy.
gets sticky.
So maybe when we get to J, I might, I don't know, it's a little dangerous to mess with things, but I think we'll watch it. If it gets closer to the edge, then we'll mess with it. But this is the dangerous asteroid, everyone. It's actually not very dangerous, so don't be worried. No,
People are gonna fund astronomy.
I could say that. I mean, this is not something to cut out, Jamaica. But so this asteroid is not actually that dangerous. So don't worry about it. It's just a way that we calculate impact probabilities. It makes things look scarier than they are. So that mirror that's in some rear view mirrors, it says objects are is it closer than they appear? Okay.
Yeah.
So for asteroids, it's a little bit different. It's like the way it works is that the probability of an asteroid hitting the Earth always goes up with time until it's eliminated, until the possibility of it is eliminated. And the reason why that is there like a little whiteboard here?
There is over there.
Well, yeah, I'd have to go over there, but let's see if I can
You can
draw.
turn your computer.
Oh, well, can you watch this? Make sure. So the reason why that is like this is a very, very simplified version of how to describe impact probability. But can you all see the whiteboard here?
Yes, we can.
Okay, this is not erasing very well, but I'll do my best. So let's say this is the Earth right here. When we predict the orbit of an asteroid, it is kind of a cloud of solutions. So when we say, okay, predict in time the position of an asteroid, it could appear here, it could appear here, it could appear here, it could appear here, or it could appear somewhere on the Earth. But it's very probabilistic. So it's actually kind of a distribution of positions where an asteroid can be at the time in which we think it could hit the Earth. And the volume of this cloud of solutions right here divided by the volume of the Earth gives you the impact probability. So you have the volume of the Earth. So the impact probability sub impact, let's say P sub I, is the volume of the Earth and divided by the volume of this cloud of potential positions of the asteroid at the time when we think it's going to hit the Earth. So this is going to be the volume of the asteroid. And so this value right here is always less than 1. Like it should always be less than 1. But right now, let's say for this asteroid, it's going to be 2% because the volume of the sphere of impact solution is very, very large, and the volume of the Earth is very, very small. So this will be around 2%. Now, as we improve the orbit of the asteroid, this volume shrinks because the scatter and the positions of the asteroids get smaller and smaller with time. So as we improve the asteroid, we get more data, we extend the orbital arc, the volume of the scatter and the solutions get smaller and smaller in time. So the numerator right here stays constant, the volume of the Earth stays constant, but the denominator right here gets smaller and smaller. So with time, this percentage is going to only go up. Say it'll go up to 4%. We get some more data solutions, it'll go up to 10%. So it starts to look very, very scary. But what will eventually happen is that the volume of the solutions will start to displace themselves from the volume of the Earth. So I'll erase this. And let's say we get really, really good data. Here's the Earth again. The cloud of the solutions will start to get small enough that it starts to only partially overlap with the Earth. And eventually, the volume will get so small that it will start to only clip the Earth, and it'll get smaller still to where it completely is off the Earth. So if we had to like draw a graph, let's say this is the probability, P sub I, and this is time. Time increases in this direction. The impact probability is going to look something like this. It's going to grow steadily with time, and eventually at some point it's going to drop off and go to zero. So that's why, I say objects in mirror, asteroids in mirror are more scary or have a higher, seem like they are, have a higher chance to impact the Earth than they eventually will actually have once we get better data.
That was a brilliant explanation, Bryce. I've never heard that before. Thank you so much.
So how are we doing? Are y'all keeping track of this? Let's see.
Yes, I am.
We're on it. We're clipping the edge, it looks like. Shoot. So I'm going to abort after frame here.
Complete.
So we're not going to take data. And because we are clipping the edge here.
Is the DRA DDEC, is the telescope tracking too slowly?
Yeah, I think it's tracking fine. Hi, Tony, just want to double check with you. Are we using non-sidereal tracking for this object?
Yeah, it's non-sidereal.
Okay. So we're going to have to do the very, very tricky thing, which is to nudge the asteroid over, which is it's very, very finicky. Let's see here. So if I'm not mistaken, if we give this a positive value, it's going to nudge more to the center. So we
Positive value in X, but you want a negative value in Y to nudge it up.
So we're going to assume that it is going to be in the center position, like this center position right here, because that was its last position. So let's see, I'm going to go to region here. I'm going to go shape. I'm going to go to ruler. So that looks like 2 arc seconds. Okay. So now I have to do the very, very tricky command here because it's always, you're not sure which direction it's going to go. MXY. So we use MXY. MXY, Y arc seconds, X arc second, X arc seconds, Y arc seconds. So we're going to use MXY and we're going to say 2 arc seconds, 0. Let's see what happens. Okay, it looks like it worked. Now let's start this all over again. So we're going to have to be very careful and be very vigilant to make sure it doesn't go off the slit. And that's just the way it is sometimes. Because sometimes the prediction of the motion of the asteroid is not 100% accurate. Sometimes it can vary a little bit. So especially because we're looking at this tiny little box here, we have to be very vigilant. But let's see here. So I wish we could do more subtractions on the fly, like look at some of the older images, because then we could see when it starts to go off the slit. Oh, it sounds like we have a visitor here. Hello, how's it going?
I'm a random Keck software engineer, but I was just given like several dozen oranges.
Oh,
Would you like oranges from someone's tree?
yeah, that's fantastic.
Take as truly as many as you can.
Oh, thank you so much.
Someone just showed up to give us oranges. This is pretty awesome.
Ooh, nice.
Thank you so much.
We're leaving tomorrow, so
Okay.
there will be
Enjoy.
limits on
Yes,
how
would
much
you
we
like
can
any?
consume. But these are for both of us.
Yeah,
so-
yeah, yeah.
Okay.
Thank you so much.
Thank you so
Enjoy.
much. Thank you for wiping my load.
What was your name? What was
Max.
your Max?
Nice to meet you. Thank you for the
Hey,
overview.
Max.
Nice to
We're
meet
on
you,
a
Max.
Shadow the
We're doing
Scientist,
Shadow the
oh,
Scientist.
wonderful.
You want to come
Yeah.
say hi?
Sure.
Yeah, come say hi.
Say hi.
Yeah, come tell us about what you do.
Max, it's been too long.
In a long time.
Yes, it
Y'all know each other?
Yes.
Oh,
I've
nice.
We ran into each other. Yes, I am a software engineer here at Keck.
Cool.
I work on data reduction. So that is taking the raw images that these guys are taking right now and turning them, well, hopefully,
Into something.
and turning them into something useful.
Yes.
So going from either lots of black with white lines on it or black with little dots on it and turning that into nice images or extracted spectra and all the stuff that scientists do their real work with. So yeah, you guys are using MOSFIRE right now, which is one of the instruments I'm working on at the moment.
And it's particularly tricky right now.
It is
as you
very,
know.
very difficult. Although actually, so MOSFIRE has this thing that lets it change its configuration all the time.
Oh, yes.
But right now, it isn't really letting you change the configuration, which makes the scientists unhappy, but makes me very happy.
Oh.
Because that's the hardest part to deal with.
Oh, wow.
That doesn't make me happy. I wish it worked properly. But
It's okay, you can be
no.
honest. You can be honest.
Well, we you know, this is part of doing science is that you have to learn how to adapt, you know, and figure out how to use things the best that they can, the current things that
Yes.
they are. So that's what we're doing right now. We're using this in imaging mode. We're actually imaging a hazardous asteroid, a potentially hazardous asteroid, in this tiny little keyhole that was left open by the CSU.
incredible.
I mean, we're making it happen. So
Is that the 2030 something?
Yeah.
2024
YR4.
YR4, yeah,
All right.
Yeah,
So we're getting
that's
some
cool
Y,
stuff.
some Y-band imaging of it.
We were very
Uh,
excited to get it.
Yeah, I mean, it's pretty astounding, pretty astounding.
Pretty faint too. So
That's
it's
really
there.
cool.
Yeah.
Glad I stopped by.
Oh, well, we're glad to have you, and
You
thank
give
you.
us oranges.
you-
we
thank
show
you
an
for-
asteroid. It's a trade, right?
Well, yeah, and thanks for all your hard work in getting these things to work. So there it is, there it be. So yeah, because we nudge things a little bit, so that looks like it could be it. We're maybe not getting the best subtraction here, but I think I see the B right here.
Yeah.
I think I'm seeing the B, and this is the A.
Oh, right. Do we need to push it a little bit?
Maybe we'll. I mean, I wish this thing had. Oh, this does have a pause button. So we'll see. We'll see the next one, and we'll see if we need to nudge it a little bit more.
Excellent. Max, thanks for stopping by. I hope to have you on a session again where we can admire all the amazing things that you do.
All right.
We'll use these for planetary references.
Beautiful.
Ah.
Wonderful.
In your honor.
All right. Have a great night.
Thank you so much.
Thanks, Max. You too. Aloha.
Thank you, Max. All right, look at this. Here we go. So that looks like it might be. Now I'll show you all another trick that we can do to kind of make things pop up a little bit more. I don't recommend doing this all the time because it can lead to you seeing things that maybe aren't actually there. But we can actually smooth images to make very slight sources appear better. Oh, it's going to change the stretch. Oh yeah, so that's actually that doesn't really help in this case, but you kind of can see something popping right there. So I did keep in mind this thing does have 0.04 magnitude variation, so it could be getting brighter and fainter as things go. Now another thing that can affect throughput is of course the changing weather. Oh, there's the volcano, but that's not quite what I'm talking about. So let's see if there is any change in the weather. Let's see the conditions, this all sky conditions. They look pretty good up there. And now I'm going to check the elixir. Elixir scatter is very, very small, still very small. It looks like it jumped up a little bit while ago, but I don't see any clouds. I don't necessarily see any clouds, but it still looks like the scatter is still very, very small. So we're about to get our next nod, and let's see, let's go to our cartoon. Now this cartoon's upside down compared to what we're going to do, so it's actually going to go down. But yes, we should see this source right here. We should see our source get dropped a little bit low. And if it happens again, what I'm going to do is I'm just going to not nudge the slid over a little bit using this move command. Maybe just 1 arc second or half an arc second, just to kind of we call this paddling. When you have to like manually keep things within a certain area of the detector over time. You make little minute adjustments, kind of like, you know, those people that do the curling, that very weird Olympic sport where people are like sweeping in front of like this giant rock to make it speed up or slow down very minutely. It's kind of like that. You're making slight little adjustments to the instrument to keep the asteroid in the field of view. wish this thing has a very small field of view because it's in this little mode. So here we go. All right.
Exposure
Fits
complete.
Okay, let's see here. Let's see the difference image. Here we go. All right. Oh, look at that. Oh yeah, it's there. It's definitely there.
Oh, yeah.
The next one is going to pop up here. So after that one, we'll pause it. Or actually, I don't know. I think it's a little risky to mess around with this. I'm not sure what that pause button is going to do. Is it going to like pause, like stop the exposure in the middle of the taking of the data? Or is it going to like pause after the next one? It's not clear what it's going to do. So to be safe, we're just going to let it do its thing. This is the largest displacement south in the negative y direction here. So all the other ones will be closer to here. So I think we might actually be good. So we'll just keep on watching it. And then we'll get over to J. And surprisingly enough, there can actually be better throughput in J. So we might actually be detecting, seeing this object more easily in J. Now I'm going to remove this moving here to make this a little bit more clearer. Yeah. So you can still see it there. You can still see it there.
Yeah.
So this object has a magnitude of about a V magnitude of 24. It's very, very faint. It's very, very faint. And when you have 0.4 magnitude variations, it can go somewhere between 24 point. I think the magnitude variations are measured in peak to trough. So it's going to be anywhere between 24.2 to 23.8. So that can be enough of a variation there. Yes, but we are going to get it, and we have the most powerful telescope right now in the world to try and get this thing. Now the other thing is we also want to check other conditions right here, so we can also see what the seeing is. Now we have a way of measuring the seeing ourselves, but using this Mauna Kea weather website, there is actually a seeing monitor. So we'll see what other people are saying the seeing is like. So this is, yeah, it looks like it's not running. It hasn't been running for a long time.
Oh.
No, it has not been running for a long time, it seems. But let's ask Tony here. Hi, Tony. How are you doing? Do you have any clue what the current seeing might be?
No. I don't have a current seeing estimate. The guide star full with max is 0.6.
0.6. Okay. So, but that can be off what you would actually see in the instrument by quite a bit. I've noticed that sometimes.
Yeah, worse than what they.
Okay, but seeing should be pretty good right now, I'd say.
I would say so.
Yeah, so right now we have maybe 0.6 arc second seeing. So that's pretty good. And looking at these all sky cameras, it doesn't look like there's any clouds overhead. So this is this is about as good as it gets for ground-based observing.
Exposure.
And we just have to keep in mind that we're doing this in the infrared, and this is a very, very faint target. So let's look at the next subtraction. Oh, I think I see it again. All right, so it looks like it's good. It looks like we got a good subtraction. Now it is moving up a little dangerously close to this chip edge. But let's say even if it does, I think we can stop the sequence and move on to J, because I think we have enough images of this in Y. So I think we probably are fine. We probably are fine. Let's see. Well, Matthew, what do you think? Do you have any opinions about the quality of the data?
I think you're too close to the edge of the slit there.
Yeah, it does look pretty dangerous. It does look dangerously close.
I mean, I think you're way too worried about the dither pattern and it ending up somewhere. You're pretty well constrained. I would be much more liberal with my use of the nudging.
Okay. Well, we don't want to nudge it while it's in the middle of taking.
No, definitely not. But I think the tracking rate overall is off, and you also want to push it up a bit. I think you're too low. You're gonna want the next move to be like MXY1, -1.
Yeah, I'm not sure what direction the up and down goes.
I figured it out. Well, if you go negative in Y, it'll be up.
Okay, so the appearance of the detection will go up that way.
Yes.
Okay. So we'll do that. We're going to abort after this frame. And we'll start doing J's. But after this frame is done, we will nudge it. You say 2 and -1, you say?
Maybe 1.51 minus 1. I would say.
1.5 and -1.
Yeah, that should be about right.
All right.
Yeah.
Yeah, there's always sign conventions and these kind of instruments.
Just looking on the right, when you put in the move command, you see how you moved from 996.1983 to 993.1985.
Yes.
You moved up 2 pixels, but that's negative in arc seconds. So moving up your target up a few pixels is negative in the MXY convention.
Yeah, so like these are both in coordinates of let's say detector plane space coordinates, not actual RA and DEC coordinates. So
Yeah.
yes, it should go by what this compass rose is saying for the X and Y.
Yeah.
Yeah, let's see. All right, so we're going to move the J's. We're going to get to J's.
You can start the move and I can click the J bit. J imaging, not spectroscopy, press no.
Oh. There we go.
Yep.
Yeah, that's a common pitfall. So I'm gonna type in the MXY command now.
Yeah, start moving while it's changing the thing.
There we go.
Okay.
All right, and yeah, I just looking at this data here. Let's check on it. Yeah, this one fell off a little bit, but I think it'll be fine. I think our movement will be we'll put it back on track.
I've set up the J 10 second 18.
Oh, did you do this? Did you put the 10 and 18?
Yep.
Okay, thank you. So we're gonna do the slit nod. Here we go.
Yeah, I think I would rather do 3 nods and then repeat 3 nods, because if you're
Yeah,
doing
that's what Josh was recommending, is that you do the 3 nods and then you displace yourself in X.
Yes.
3 nods again.
Yeah, I think 5 is too many.
Yeah, and we have a little bit more. It gives us a little bit more flexibility. We don't have to worry about running into the edge of these things. But I think the min and max is about the same, because you divide it's the slit length divided by the number. So we'd have to also we'd also have to lower the slit length here, the slit length parameter.
I mean, the slit length is fixed, so it just divides it by 5 or divides it by 3.
Right. So we want it to be more compact. So we want to also decrease the slit length.
Maybe, yeah. But I would definitely be doing 3, because that seems to be the amount of time before the target starts moving off. So I would not be doing 5.
Okay, yeah, we'll stop it after 3 and change it to 3 and then redo it, while also telling it to nudge over a little bit. So I'm quite curious to see how this goes. What's it going to look like? What are the J's going to look like? Do we have any bets? Are we going to see a clear, nice detection, or is it going to be kind of smudgy? Because sometimes I've seen objects look better than J than in Y.
Yeah, J and Y are comparable, but Y is more sensitive to Y is better when the atmosphere is really good.
Laura May, what were you going to say?
Make attendees take a vote.
Laura May was saying make people take a vote. I don't know if that's
Um,
possible.
we could do that. No.
Oh, no.
Oh my gosh. And you know, I realized we've stayed an hour over. So I really appreciate you all letting us stay a little bit longer to experience this with you. I'm so very excited that we all got to share and you capturing this infamous asteroid.
And thank you, Jamaica, for staying longer as well, because
Yeah.
you're on Hawaii time zone. so-
Yeah. Thank you
Absolutely.
so much, Jamaica. And yeah,
Yeah.
you've been a great host to us.
Thank you. Thank you. It's been a
Thanks
pleasure.
again for the lays. They smell beautiful. They smell wonderful.
Wonderful, wonderful. Well, we have a few more questions in the chat before we leave, if that's okay. So we have one.
I think Laura May can answer this question. Sorry, Laura May, to bother you. There's
All right.
someone's asking a question in the chat. Do you want to answer it?
What's the question about?
What effect does moonlight have on IR imaging?
Oh, it's very interesting. We were just discussing. that.
Yeah. We were just talking about this.
So, we basically will often do IR imaging during when it is close to the full moon. It's something I'm kind of sad about because I've never seen properly the Milky Way above Mauna Kea. And the difference when the moon sets up there is striking. Like it
Yes.
is pitch black. You open the door to the scope and you can't even see your hand in front of you when the moon has set. But yeah, because we are in IR and infrared, we can do our work when the moon is out because the moon is reflecting the sun's spectra. And so it doesn't really affect us. Did I explain that correctly?
Yeah.
There's-
So the
yeah.
solar the peak in the solar spectrum is about 550 nanometers, and it drops down precipitously past 800 nanometers. I see if I can get a picture here. So yeah, oh, this is in nanometers. How convenient.
Yeah.
So the peak is around 550 right here, and the longer wavelengths you go, the fainter and fainter I guess the fainter and fainter I guess it drops off quite a bit. So at infrared wavelengths, the contribution is not 0%, but it's a lot less
No.
compared to the visible. So the moon is more or less reflecting the sun's light, the solar spectrum. There are differences. There are features in lunar spectra that can make it not completely a perfect reflection of the sun's spectrum. There could be absorption. There can be emission of certain features. But in general, asteroids, it goes for asteroids as well. The moon and asteroids reflect the sun's light, more or less have the sun spectrum. So in moonlight, you're more or less getting sunlight. It's a lot dimmer, but you are getting sunlight. But it follows the same principles. As you get to longer and longer wavelengths near infrared, the contribution is a lot less. So at infrared wavelengths, the sky background from the moon itself, from moonlight, is a very, very small. It's very, very minimum. And the longer you go, it basically drops off. So that's why in full moon we use infrared instruments. And it also means that in dark time, you have a very limited amount of time to use optical instruments. So in general, dark time for optical instruments tends to be a lot more contested when astronomers are writing proposals and fighting over who gets the time. Optical time during dark time is more scarce. But infrared, we can observe any time of the month. We can observe dark time, we can observe bright time. So in general, we like to let the astronomers using optical instruments have the dark time, and we use the bright time.
Got it. Rob says, thank you. And yes, thank you. Let's see. One more question here. When was the last time you found organic material or water on ice, on comets, asteroids, meteorites, any of you?
All the time.
Yeah, there you go, yeah, hey, Matthew.
Yeah, I mean, every time we get like a spectrum from James Webb and we're looking at one of these asteroids, we're
Do you want to
finding.
show them a spectrum?
Sure.
Yeah, so I'll stop sharing and you can share a screen when you're ready. Or actually, are you capable of sharing screen?
Should be.
Okay, I'm going to stop screen sharing here, and you can why don't you show them a JWST spectrum? Okay, it looks like we got it, but I think we've got to move over a little bit, and it might be a little bit too low. See, this is the target.
So do you see my screen here?
Yes.
So here's actually a spectrum that I got from James Webb a month ago or so. It is the spectrum of Nereid, which is a irregular satellite of Neptune. And, you see features of very abundant water ice, which is at 1.5 microns here. You have this little plateau here, which is indicative of crystalline water ice, in fact, because in the outer solar system, you actually have crystalline amorphous water ice, which are two different types. And then you have this 2 micron, which is what I was trying to see today on a Centaur by getting the spectrum. Then you have this giant absorption here where, the reflected light, this is the y-axis, this reflected light, drops almost to 0. And we sort of from the ground can only observe in this range right here from 1 to about 2.4. This here is inaccessible from the ground, period. This part is very difficult. And this is, again, inaccessible. So here we have CO2 ice, this little divot right here, which of course, there's CO2 in our atmosphere. So you can't see the CO2 on other things, right? If our CO2 is blocking it. But right here, it turns out you can very effectively see the CO2. And I'm just comparing it to a spectrum of a very water icy Kuiper belt object. So this one has so much water ice that you're seeing no reflection at 3 microns. So there's a wavelength of light at 3,000 nanometers to 3 microns, at which water ice is totally like not reflective. So it just absorbs all the incoming light in this part of the infrared. And so I am trying to figure out what is the origin of Nereid's very strange satellite. It has the most eccentric orbit of any satellite in the solar system, period. And yeah, it's been a mystery for a few decades now. People have been really thinking about it. And my advisor got the spectrum of this object nearly 3 decades ago now in 1998.
Wow.
And he saw this feature and he's like, that looks weird. It's kind of a deep feature compared to some of these other Kuiper belt objects. And well, it turns out it is kind of deep compared to other Kuiper belt objects, though not this one. This is one of the ones with very deep ones. And so, we can do I have a comparison? Yeah, so other irregular satellites and Kuiper belt objects, they don't have nearly as much water ice right here. In blue and black, there's barely anything in terms of the water ice.
Oh, wow.
Right. And this one has much more abundant CO2.
That's awesome.
So these are sort of things we see now, thanks to James Webb on a daily basis, whereas before it would take decades of observations of single targets and beating, at signal to noise from the ground. And now this is, just so much more accessible and so much more doable. Of course, ground-based instruments are catching up and everything, but James Webb is going to be the workhorse of solar system astronomy, spectroscopy, that is, for the next decade. So this is exciting stuff.